Now let's solve a question related with the joint distributions. It's going to be a rather involved question in terms of the algebra that we are going to be using, but it's very straightforward in terms of probability. All right, so given random variables of x and y with x greater than 0 and x smaller than y, the joint probability is given with this formulation. C is equal to exponential minus 2x minus 3y. The question is going to consist of a couple of parts. First, determine C. Note that I could have easily skipped this part and I expected to find the C and continue solving the question. But anyway, so let's give a scenario to this question so that it's going to be easier to understand what this question may correspond to in real life. You may think about this x and y, especially this condition. X is smaller than y and x is going to be greater than 0. Hence, automatically, actually, y is going to be also greater than 0. So let's see. Now, this may be, x may be, let's say that you make a phone call to a station, right, or to somebody, and you are connected, but you are going to wait for some time to be connected to the correct person. Usually that's the case when you make a phone call to some of the companies that are related to some, let's say, cellular phones or things like that. So x may be the time that it takes for your phone to be answered, and y may be the time it takes for you to be connected to the right person. Note that x is surely going to be greater than 0 because it should be a finite, it should be a positive time required to make the connection, and y is going to be surely greater than x because the first part, actually usually it's an automatic answering machine which answers your call. Then you are being routed to the person that you or the department that you call. Therefore, y is going to be greater than x value. That may be one interpretation. You may think about any scenario that you like. And the resulting thing is actually, as you can see, it is an exponential distribution, but it's a multivariate one. Therefore, those interpretations related with time also seems to be pretty much in sense or consistent with the exponential distribution that I talked about previously. All right, first determine C. Now we can directly continue with the algebra, but as I said previously, it's always a good practice and it's always a good idea to visualize the distribution. This time it's going to be in 3 dimensions. Now this is going to be what the distribution looks like. This may not be very easy to draw, but actually if you are comfortable with exponential values, starting from 0 to going to plus infinity, which is going to start with a non-zero value, it's going to be take the highest value at that point when x is equal to 0, and it's going to decay to 0 as x goes to infinity. And we have the same thing here. You can plot this. I showed this, I plotted this on MATLAB so that it's going to be as good as it can see. So actually here, this is the y-axis and this is the x-axis. It increases 0 to 1. Actually, it doesn't stop at 1, but I just concentrated up till 1 here, and it goes here in this direction and in this direction. And there you can see an exponential decrease here. Here actually it has exponential decrease, like on this surface, you have different exponential decreases for different values of x, right? Or you may think from the other perspective. You may also think from this perspective. There's also an exponential decrease in this region. One important point here is there is not going to be any probability. The probability density function is going to be 0 when x is greater than y value. X is equal to or greater than or equal to y value. So this is the actually boundary of this probability density function. Actually, it's difficult to visualize in 3 dimensions, but you may see this as another surface. So probability density function does not pass here. Actually, in this part, in this region, probability density function is equal to 0. you may easily think about in this fashion. So probability density function is only a non-zero value in this part. For the rest of the region of x and y values, for negative values or this condition not satisfied here in this range, it's going to be all zero. All right. So determining C is basically based on finding the volume here beneath this surface, right? It's going to be the volume here, all the part beneath this surface, as I think you can understand. So the volume here is going to be equal to 1, because this is the property of probability, joint probability density function. So what we are basically going to do is we are going to write the double integral, minus infinity to plus infinity, minus infinity to plus infinity, fxy xy is going to be equal to 0. Of course, integral, because we are dealing with continuous variables. Now, instead of this, let's write c is a constant. You can take this out. It's going to be minus 2x minus 3y. Now, the very important point. What are going to be the limits, and which one is going to belong to x and which one is going to belong to y? So, one option is to write this way, from 0 to infinity, and this is going to correspond to dy. And for the inner part, I'm going to be using, of course, dx, here x. Now pay attention, this is the important part. X cannot be 0 to infinity. If this were 0 to infinity, then we would be talking about this whole quadrant here, this surface here, this first quadrant. Positive values of x and positive values of y. This is not the case. We are only given permission to integrate for this region. So for when x is equal to y, this is the region up to which we can integrate the x values. So actually, for instance, if you are at that point, let's call this point y, and let's integrate over different values of x. This x is going to start from integration of 0, and it's going to stop here. And what is this point equal to in terms of x? Note that since x is equal to y, this is going to be y. And the logic is y can go start from 0 and it's going to go to plus infinity. But at any point of y, the value for the x values, let's call this another y prime, this time it's going to be y prime, we can only integrate x from 0 to y prime here. Therefore, integration of x is, the integral inside can be between 0 and y. This is the very important point. If you are not comfortable with this, you may of course ask me, but you can go back to your notes related with the second, I think the second mathematics course you have taken. Anyway, so this is going to be basically 0 to infinity. Let's see, I'm just going to copy from my notes because it's a very easy integral to make a mistake. So I think it's going to be something like this. Let's see, it's going to be, if you take, it's going to be 1 minus 1 over 2. All right, and x is going to be from 0 to y, and this is going to be dy. So if you take the integral here, this is going to be the result. If you take the derivative with respect to x, it's going to be minus 2x. These are going to cancel each other. So this part is going to be minus 1 over 2. Of course, we have c here. So maybe it's a good practice to get rid of this minus 1 over 2 here to make this easier. Minus c over 2 is going to be. So this part is going to be equal to exponential minus 2y minus 3y, right? Minus exponential minus 2 times minus 3y. All right, so this is going to be 0. This is going to be simply exponential 5y minus exponential minus 3y. So what we are going to have here is going to be minus c over 2 from 0 to infinity, exponential minus 5y minus exponential minus 3y dy. And if you continue using the same thing, it's going to be minus 1 over 5 exponential minus 5. And it's going plus 1 over 3 exponential minus 3y. And it's going to be from 0 to infinity. And this is going to be equal to, actually, let's see, it's going to minus 1 over 5. When you put infinity here for both cases, it's going to be 0. So we are going to be only interested in putting 0. There's another negative sign here. So it's going to be c over 2 minus 5 over 5 plus 1 over 3. And this is going to be equal to, if I can see from my notes, let's see. It's going to be equal to 1 over, is it 1 over 15? Let me see the whole thing. It's going to be, minus 3 plus 5 over 15. Yeah, it's going to be 2 over 15. So it's going to be c over 15, which is going to be equal to 1, and c is going to be equal to 50. So we got the probability distribution function of this. The joint probability distribution function is going to be equal to, it's going to be, 15 exponential minus 2x minus 3y, and the support of the variables random variables x is greater than 0 and x is smaller than y. So this is the description of our random experiment. All right. What is the probability that x is smaller than 1 and y is smaller than 2? Again, it's a good practice, and I think for this question especially, it's a very good practice to show the whole thing on a diagram, again on the graphics. So what we are interested here is the region x is smaller than 1. So where is our x? Here it's going to be here. And y is smaller than 2. So y is going to be smaller than 2, it's going to be this region, and x is smaller than 1, it's going to be this region. So it's going to be this. So it's going to be the volume here. All right. So if we find the volume here, we are going to be finding this probability. Now, it's usually a very good practice to look for to this distribution from a bird's eye point of view. Now, I just, so in this case, the coloring here, the coloring is yellow, is the highest probability density function. The rest is red, the probability density function drops down. And here we can see x and y. And I have shown you here the domain of this, or the where this probability is required to be found. X is smaller than 1, it is this region, and y is smaller than this 2. So we are talking about this region. Note that it is the very same region, this region I'm talking about, because I look from this bird's eye perspective. So what we need is, we need an integral over this region. We should be careful about that. Again, this is not going to be an integral consisting of constant boundaries. Why do I say so? If this were a rectangle, then we would be able to say so. Think about this. If this were a range, something like this, or a region like this, we would be integrating y from 0 to 1, right? Because for each x value is 0 to 1, and x from 1 over 1.2 to 1.6 for each y value is the same. So the integral could have been easily 1.6 for y dx, and for dy it would be 0 to 1 dy. It would be that kind of an integral. That's great. But unfortunately, this is not the case for different y values. Here we are going to have different x values. And moreover, the change or the upper limits that we can come up with a formula in the previous question, in this previous case, note that we have come up with a formula where x is represented y. actually this is also tricky because this also changes with respect to values of x and y. Up to this point, the relation is x is equal to y relation is conserved. Unfortunately, from this point on, the upper and lower limits takes a different form. Actually, we have a rectangular form here, the nice form, the constant limit form that we like. So the method I recommend, you can do anything because it's totally a mathematical, this is totally an algebraic solution that we are talking about here. I prefer this one. I take the limit of 0 and 1 and I take this x. So x is going to be between 0 and 1. So it's going to be an integration of x between 0 and 1. Then when it comes to y, it's going to be, now note that x is going to be between 0 and 1, and y is going to be equal to from x to 2. Let me write the whole thing, then I'm going to talk about the rationale in a minute. So here is the logic. We are at any x value. Let's say that we are here. X is equal to 0.4. Now, first I integrate with respect to y from x to 2. From x to 2 is going to be, note that since this is the value of x, this is also going to be equal to x. I'm going to be integrating in terms of y from x to 2. So it's going to be this very thin strip which is integrated. And so this is going to be working for all values of x. If you are here, then I'm going to be integrating here. Even actually, if you are here, this is still going to work. Because we are at this point here, x, we integrate from x to this value. So this whole region can be integrated in terms of y, we can integrate in this fashion. What about the values of y? What about the values of the integration limits of x? We are going to be integrating x from 0 to 1. Actually, if you may think about that way, x is here at a very small value close to 1. Therefore, so it's here, let's say, the integration is what y is going to be this very small x, call it x1, from this x1 to 2. That's great. X a little bit higher, to call it x2. Now, it's the corresponding y is going to be x2 to this point. So by this way, we can span the whole region. Now, this shows that this works. On the other hand, why only this works? You need to think about a little bit. So for instance, you can ask the question, if we invert the order of x and y, wouldn't this work? As far as I can see, no, this would not work. It depends on the shape of the region for which we would like to make the integration and find the volume over that region. So actually, you should use your heuristics and you should use your knowledge about algebra and come up with an easy method. But if you like, you can divide it into separate segments and write an integral to find the volume over this region and write another integral to find the volume over this region. Do whatever you like. This is the method I prefer. Anyway, now it's going to be a total integration, nothing fancy here, but let's see, it's going to be 15 is here, exponential minus 2x minus 3y integrate with respect to dy. So it's going to be, let's see, minus 1 over 3 exponential minus 3x 3y from x to 2 is going to be dx. And all right, we can get rid of this 3, so it's going to be minus 5 exponential minus 2x minus 3 times 2 minus exponential minus 2x minus 3x dx, and we have x0 to 1. And this is going to be exponential minus 3x minus 6 exponential minus 5x. I hope I did this correctly. Yeah. So let's continue. This is going to be minus 5 x minus 5 minus 1 over 2 exponential minus 2x minus 6, and we have plus 1 over 5 exponential minus 5x 0 to 1. And let's go a couple of steps further. It's going to be minus 1 over 2 exponential. If you put this here, it's going to be exponential minus 8, I guess. Yes, it's going to be minus 8 plus 1 over 5 exponential minus 5. Then it's going to be minus 1 over 2 plus 1 over 5. And if you do, I'm going to skip a couple of steps. If you do everything correctly, which is very little to do, so we have this much probability, which is very close to 1. And it makes sense, as you can see, this region is, this region is, as you can see, the probability density function. Now the real value of C is written here, as you can see, C is equal to 15. As you can see, most of the probability density function has died out for the rest of this range. Okay, probability of x greater than 1. Now for this one, I'm not going to be using the figure, but if you like, you can do it. What we need here is note that now this is actually a variable, a question about a single random variable. So we need the marginal density function. So what we need is this quantity. And in order to compute this quantity, what we need is to write the, again, probability density function minus 3y and integrate this. And again, the question is, what are going to be the limits? Using the previous diagram, actually, the graph for the figure for the previous question, the limits are going to be from x to infinity. I'm not going to talk about the reasoning because it's similar to the previous one, and I'm just going to write a couple of steps. Here is going to be minus 3 exponential minus 2x times exponential minus 3y from x to infinity here, and the result is going to be 5 exponential minus 5x. Now let's analyze this. First of all, we are going to realize that this is not the complete description of x yet. But first of all, let's analyze this function. As you can see, this function does not contain any term related with y. Is this supposed to be so? Yes, because as you can see, this is basically a function. And this is actually a certain probability density function, but it's a function, and it's a function of only x. Why? Because we got rid of y by integrating all possible values of y. And note that this is not sufficient representation. Note that we should also write here as x is greater than 0. So this is the domain of x. So if you were to plot this probability density function here, it would be x is greater than 0, so it's going to be decreasing in this fashion. So we have x here, here we have fx here. This starting value is equal to 5, and note that this is an exponential, so x is an exponential distribution, and this is lambda is equal to 5. So its parameter, let me write it like this, lambda is equal to 5, whatever this thing is. This may be minutes to the power minus 1 or second to the power minus 1, but this is how x is distributed. So it really makes sense that the scenario that I talked about, being phone calls, seems very much plausible. Now probability of x greater than 1 is simply this region here. So it's going to be 5 exponential 5x from 5 to plus infinity. But if you also recall from exponential distribution, this is going to be easily found. We know that the integral is going to be found as exponential minus 5, which is going to be equal to 0.0067. So it is this probability. Well, as you can see, this is not a very good scaling, but it is this probability, a very low probability. All right. Okay, the next question is to find the expected value of x. To find the expected value of x, we need the marginal probability density function, which we have already found in the previous part as 5 times exponential minus 5x, and note that the domain was x greater than 0. So but here, to find the expected value of x, we need to integrate x between 0 and plus infinity 5 times exponential minus x. This is the probability density function multiplied by x, integrate over dx. Let's take this 5 out to see that this resulting integral is going to be performed using a technique called integration by parts. This is what we call u, and this is what we call dv. So u is going to be equal to x, du is going to be equal to dx. This is the first part, and the second part is going to be dv is going to be exponential minus 5x dx. So we integrate both sides. Indefinite integral here, this is going to be v is equal to minus 1 over 5 exponential minus 5x. And this integral itself, so again the general, if we integrate u dv, note that this is now a definite integral, so be careful about that. We are going to be using limits. uv between a and b minus gain a and b v du. So using this rule, with that information at hand, we can come up with the result. This part, therefore, is going to be equal to u times v. So it's going to be minus 1 over 5 x exponential minus 5x. But note that this is going to be evaluated between 0 and plus infinity. Minus, again from 0 to plus infinity, we have v times du. Where is our v? It's going to be minus 1 over 5. So let's put here plus 1 over 5 here. It's going to be exponential minus 5x. And u, where is the other term? Du is dx. So this is going to be dx. Let's first handle this part. It's going to be minus 1 over 5 exponential minus 5x from 0 to infinity. This is going to be equal to plus 1 over 5 here. And multiplying with 1 over 5 here, this whole expression is going to be equal to 1 over 25. Now let's handle this part not this time, especially concentrate on this part. Now we have here an x, an exponential minus 5x. Now x will go to infinity here. Exponential minus 5x will go to 0 here. So the question is, which one will it go to, infinity or 0? So the thing is that it depends on whether which one is faster compared to the other one. So when and x goes to infinity. Now note that exponential faster is exponential function is faster than a linear function of or any polynomial function of x, but let's also prove this. So what we are searching for is this limiting value, plus infinity x over exponential 5x. Now when you put infinity here, both of the terms are infinite. So actually there is actually, as I said, two series which go to infinite, but it depends on which one is faster. So for those cases, we'll use the L'Hopital rule and take the derivative here and compare the derivatives. So therefore in this case, limit x goes to infinity, derivative of x is going to be equal to 1, and derivative of this term is going to be a denominator 5 times exponential 5x, put infinity here, this is going to go to 0. So the upper limit when put here is going to be 0. When you put lower value here, because there is x here, there's going to be another 0 term. So from this part, actually contribution of this part to the summation is going to be equal to 0. Therefore, the expected value is going to be 1 over 25. I'm very sorry. It's going to be 1 over 25. We had somewhere a 5 here. Yes. I just saw in the last minute 1 over 5. Yes. one should be always careful with those derivations, which I'm not, as you can easily see. All right. So the last question is going to be a conditional expectation question. It's going to be what's the conditional expected value of y given that x is equal to 1. Now let's materialize this question, what this corresponds to in real life. Let's rely on the scenario I've talked about previously. X is the first time that I'm responded by an automatic answering machine, and y is the time until from the time I have made the call, from the 0 origin time, the time it takes for me to connect to the right person. So there's two things that need to be considered here. First of all, we are going to perform this integral over a certain time that I'm going to be talking about. This is going to be the form. Y is going to be multiplied by or weighted with respect to the conditional probability density, is conditional probability density function, and integrate over dy. And y is going to be, note that y is going to be due to the condition that y is going to be greater than x. X is given to be equal to 1, therefore y is greater than 1 value should be considered. Therefore this integral should be from 1 to infinity. So two things to consider. I think this is the very obvious one, but the second one, this one may be a little bit difficult to see. I repeat again, the conditional probability density should be used here because actually some value of x is given here. And what does this entail? It means that y cannot be smaller than 1. If no information about x were given, then we would be able to also take into consideration y values smaller than 0, which will shift or pull the expected value of y closer to 0. But think about, since you have already waited for 1 minute, what's going to be the expected value of y starting from 0 value? So therefore, starting from my call, y is going to be greater than 1. So what we need is to compute this value. And to compute this value, we go back to the relations related to conditional distribution. And the conditional distribution of y, given any x value, for the time being, I'm not going to write x, the corresponding value of 1, so that you are going to see the resulting function more clearly. It's going to be fxy evaluated at given values of x and y, which are actually that value and that value, although they are not defined yet, but they are specific at those values, divided by marginal probability density function of x divided at the same x value, this x value. Now, this one is the joint probability distribution function, which we have already found as exponential minus 2x minus 3y. Divided by, this was marginal probability density function for x, which we have found in part C, I guess, minus 5x. And let's go one step further. If you subtract, well, this is going to be 0 when you subtract exponential minus 2x from minus 5x. It's going to be 3 times exponential 3x minus 3y. Now note that let's first analyze the resulting form of this conditional probability density function. Actually, it was supposed to be only a function of y, but here, as you can see, it seems to be also a function of x. It is, because I haven't defined this x value yet. This is the very reason. Note that the reason why this looks like this form is because I will specify a certain value of x. Note that the very important distinction between this form, which is 15 exponential 3x minus 3y, this joint probability density function. In order to find probability, I give specific regions for x and for y. I integrate for x between two limits, and I integrate for between two limits. On the other hand, when it comes to conditional probability density function, since conditioning here is upon x, I'm not going to give a range for s, but a specific value of x. What do I mean? Since in the question it says x is equal to 1, I'm going to be converting this probability density, conditional probability density function into this form by placing 1 instead of x. So it's going to be 3 times 1 minus 3y. This is the probability, conditional probability density function of x. But note that it is not over yet. It's not the complete picture. We also have to use this rule, which comes from joint probability density function. Since x is given to be 1, y is greater than 1 is also the condition with this probability density function. So in order to find the expected value of y x is equal to 1, it's going to be equal to, from 1 to infinity, dy integral. It's going to be y multiplied by this integral. This probability density function, which is the conditional probability density function. 3 minus 3y. So actually, this time I'm not going to go over steps. I'm just going to write the result. It's 4 over 3. Well, it kind of makes sense because, it should have been, first of all, the first check is 4 over 3 should have been greater than 1. And it is. After that, we don't know. Of course, this is not a check that this is the correct result, but at least it couldn't have been 3 over 4. And one final point, if you would like to plot the probability density function of conditional probability mass function of y when x is equal to 1, it's going to look like this. This is y, and this is a conditional probability mass function of y given x is equal to 1. All right, this is the correct representation. So y should be greater than 1. And when y is equal to 1, you note that this is going to be exponential 0. So it's going to be exponential 0, 1. So the highest point here is going to be this. Then this is going to be an exponential decay. What about the rest? Here, this is going to be, well, actually, there are no fluctuations, but I just showed that on this horizontal line, we have the 0 over here. So this is going to be our probability density function, conditional probability density function of y given x. So it's going to be 0 up to y is equal to 1. Then it's going to show an exponential distribution. But as you can see, this is not exactly exponential distribution because the form of the exponential distribution, lambda times exponential lambda x, or let's say here z, so that we are not to be confused with y and x. So what can we do to make this look like this exponential distribution? Actually, as you can see, this part is the exponential distribution and it starts at 1. So what we are going to do is a very simple transformation. I define z to be equal to, let me use capital letter Z, is going to be y minus 1. Actually, wherever I am responded to by the correct person is going to be y, I'm going to be only interested in y minus 1. So the additional time of waiting after I've been answered by the automatic response, automatic answering machine. So when you put here fz when x is equal to 1, z is going to be equal to 3 times exponential 3. Instead of, well, I can write this expression as 3 times 1 minus 1. And this is going to be 3 times y minus 1. And instead of y minus 1, I'm going to be writing minus 3z. Well, actually, due to the relation between those two, there's going to be also a derivative of 1 here, which is not going to change anything. This part, this change of variables is actually related with also the concept of distribution of the function of random variables, which was a bonus video. So this part is maybe a little bit also bonus related with those transformations. But at the end, what you see here is the distribution of z is here exponential distributed with a lambda value equal to 3. And in this case, it's going to correspond to this part of the distribution. So if you just move the axis here and call this z, this time it's going to be, this part is going to be 0. And here is up to this point, distribution is 0. Here, this is going to be distribution of z. Okay,